Hey everybody. So today we're going to be talking about how I would go about creating a scene, and in this particular case, a kitchen scene that's of a particular dimension. Obviously we have a floor plan, but I'm going to show you how I would choose a shot, develop that shot, and accurately draw it in three-point perspective. So at three-point, something to note about three-point perspective is that we are not looking square with the image like 1 point. We are not looking square to the ground like 1 and 2 point. We are no longer squared to anything. And the only point in space that we know about is the point where the center of vision or the line of sight meets the picture plane. That is the only space that we know that exists, and that is the point where we have to measure from. So knowing that and having a good idea of what a three-point perspective image consists of, or the construct or the perspective system that we're using, knowing what it consists of, I can quickly gauge what I want in an image. But for you guys, I'm going to step by step walk you through this. The first thing we have to do is we have to create that perspective system in its very basic essence. Now, one thing to note when we do create this basic setup is that the center of vision, the location of the center of vision is dependent on how far away the Z is away from the true horizon, and also how shallow the angle is between the true horizon and either the right or the left horizon. Okay, so I'll give you sort of an example of this. The first one we're going to do is an example of a perfect isometric triangle. I'll show you actually two, because these two exist. Not independent of one another. They exist at its very basic essence of what it means to be three-point perspective. So just really quick, we'll just sort of run down, give you a rundown on some of this stuff. So the flat line in the triangle that you create for three-point perspective, which three-point perspective consists of three horizon lines, both the right, the left, and the true horizon. So the flat horizon is the true horizon line. The left one, regardless of which side it's on, will be the left horizon line. And the right side, regardless of whether we're looking up or down, is going to be the right horizon line. Now there are three more lines that we get from these, and those lines are going to be our reference lines. We know that the left corner is always X, so the left corner is always X, or what we would call the left vanishing point. So this is either the left vanishing point or the X vanishing point. So I'll just put an L there. And we know that based on our previous lessons that we have Y, or the right vanishing point. So this bottom right hand corner on the perspective system looking upward is also the same. So it's Y, or the right vanishing point. And then we have Z. Z is always the lone wolf. So we have Z, or the vertical vanishing point. So we have Z, or the vertical vanishing point. Now, the whole time I've been teaching you guys perspective, we've always had an X, we've always had a Y, and we always had a Z, or we always had a left, a right, or a vertical, except in single point perspective, the depth would actually be X. So in 2 point we have left and right, and in 3 point we have left and right, which is why I stick with the X, Y, and Z mostly, because X is actually the only vanishing point in single point perspective. X and Y are the only two main vanishing points in a 2 point perspective system, and X, Y, and Z are the three vanishing points in a 3 point system. Alright, so with that said, we now have X, Y, and Z. I'll just show you what we have to do in order to create our 3 reference lines. So we know that reference lines are used for receiving foreshortened units from a measure bar using a measure point onto the reference lines. So the reference lines are the only lines in a perspective, in the perspective system that we're working in, that can receive units foreshortened from a measure bar using a measure point. Now, I might have multiple measure bars in a scene, which means that for each vanishing point I might have multiple, I'll have a reference line per measure bar. So, but we can get into that later. In 3 point, however, we have 3 main reference lines. Okay, one is the XREF. The XREF starts up here at X, and it's 90 degrees where it meets the opposite horizon, and we're going to call this point A. The right reference line, or Y, is the same. It starts at Y and meets at 90 degrees on the opposite reference line. We're going to call this B. So X meets with A and Y meets with B. And as you guessed it, the Z reference line also goes from Z and meets at the opposite horizon at a 90 degree, and we call this point C. Okay, so what you should get, no matter how your triangle looks, is you should get all 3 of these points meeting together. Obviously, I'm just sketching this in so they didn't meet in the center. If I was doing this accurate, they would all meet directly in the center. And this is what we've been using from day one. We've always had a center of vision. The only difference is in a 2 point perspective construct, the center of vision is at the horizon. But we're no longer looking directly at the horizon. Our vision is no longer parallel to the ground. We are now looking either up or down. And in this particular case, because our center of vision is below the horizon, we are actually looking downward. Let's do the same thing over here. I'll try to be a little bit more accurate. So we have A. We're meeting X with A, and we're meeting, sorry, this is my off angle here, meaning Y with B, and we're meeting Z with C. So notice that X, Y, and Z are all meeting at the corners, and A, B, and C are meeting 90 degree at separate horizon lines. They're opposite horizon line. Okay, so it's the horizon line that they're not connected to. So notice X is connected with the left and the true. It is not connected with the right. It meets with the right. So X, the vanishing point, is connected with the 2 that it doesn't meet with on the other side, and the opposite horizon is where it meets. So this is very important. Notice that this is our true horizon down here. So we got our true horizon line, our right horizon line, and our left horizon line. Okay, because we have 3 different horizons. Our true is always the one that we will have 2 vanishing points associated with in our scene, and it is the one that is parallel to the ground. So off in the horizon, if you go to a beach and you look off in the horizon line, no matter how high or how low you are to the ground, the horizon line will always end at the end of the water body. And the higher up you go, it's just the more you can see, or the further you can see, that's all. But it still ends at the horizon. Well, when we're standing on the ground, no matter how high up we are, our eye line is still here. So our head will still be at this level, right? So let me draw a little fake dude here, right? So this guy, he's just chilling, and his eye height is right here, but he is now looking upward. And this is the picture plane, right? So if this is, I just did sort of a side view, and now he's looking out into the distance, and the center of vision is the only place along the picture plane that we know exists at a certain distance from the eye. So you don't have to worry about that. That should be something that you already are aware of. We could also do the same thing over here. So let's do that. So the eye level is at the horizon, but we're now looking down. Sorry, it's at a weird angle for me on the tablet. So we're now looking down, and then this is the picture plane at an angle from the character, and but still the ground is here, the eye line is here, and the picture is just at an angle now. It's always perpendicular to the line of sight, and it always meets the picture plane at the center of vision. The only difference is that the horizon is still parallel to the ground that the character is standing on. We're just looking in a different direction now. So I'll leave this guy here. Just so you guys can see. All right. Guess we could do the same over here just to reinforce this. So actually, since it's the same, we can reuse stuff. Yay for reuse. All right. So the left one with the point Z pointing down is looking down. With the Z pointing up, it's looking up. All right. So with that said, so we've got sort of the basics down, but we don't quite know how to tell this distance yet, right? So the distance between the eye and the picture plane, we haven't gotten there. We haven't gotten there yet, and we have to know how to do this. The easiest way to get this is to start with only one reference line, okay? So let's start with the X. That's what I usually start with. In order to find the distance line, it is no longer from the center of vision on the horizon line going down and then finding the station point. It's no longer like that. So think of this as having been up there, but now it has been swung down from X, from this horizon. It's been swung down like that, and still the station point was also swung down, right? So the station point or the distance line is always 90 degrees from the line that the center of vision meets with, right? So in this particular case, the center line will meet, or the distance line will meet with the center of vision, right? So this is our CV. I just want to make that clear. Our CV is right here. So now, in order for us, because we work with the center of vision, we don't work with the horizon line in this particular case. We still need to find a 90-degree angle from the center of vision. Now I'm just creating an arbitrary line or a line that's of an arbitrary length that's 90 degrees from my left reference line. Okay. Now here's where it gets a little bit tricky. And this is, I'm going to use a little trick. We're just going to create an L shape. Now I use an L shape because it's 90 degrees. We have 90 degrees separation between the right and the left line. We know from 2-point perspective that this is how we actually turn objects in space. We go from the eye, so wherever the eye is at, and then we make a 90-degree angle from there based on the rotation of the object. Now, since we already have vanishing point 1 and 2, this is for each reference line, we have left vanishing point and right vanishing point. Since we already have that for each reference line, all we have to do is make sure that this line here and this line here meet the left and right points, while this position here is aligned with that line right there, with the distance line. So it's sort of, I think this is the hardest part for most people. So what I do is I'm reverse engineering the station point. The difference between 1 and 2 and 3-point perspective is 3-point perspective has a predetermined distance that you will place the station point at, whereas in 1 and 2 you can place it anywhere and then along the distance line and then calculate your left and right vanishing points. Or in single-point perspective, just knowing where your vanishing point is at, right at the horizon, right where the line of sight meets the picture plane and the center line. Because we already have all these things predetermined, it's easy for us to calculate our measure points from there and our vanishing points. But because we're in 3-point and we've already decided the length of our horizon lines, that means that we already know the length, or we already know the angle at which the eye, which objects are at the eye, because we already have our left and right vanishing point. So basically what I'm doing is I'm making sure that the 90-degree angle point is along the distance line, because the eye, or the station point, has to be along the distance line. And then I'm triangulating X and A while all three of these points meet, and then that will be where my station point is. Now I would do this for every one of my reference lines, or like what I'm going to do here, since I already know this and I've already found my half kite. I like to call it a half kite because I see patterns much easier than I see technical math stuff. And so if you notice this, for this reference line, I have this like symbolic half of a kite. And notice how it's also facing down. So the X and the Y will have a half kite that's facing down when we're looking down. For the X and the Y, when looking up, the half kite will be looking up for each of these two reference lines here. Okay, so for each reference line, we now need a distance line. And the distance line will always be the same no matter how weird your triangle gets. So if you calculate it for one of your reference lines, then you'll be able to tell the length of it for each of your other reference lines. So for this one right here, let's just say that 90 degrees from the blue reference line, which is the right reference line, and then I take this distance and then I just apply it here, right? So this would be the distance line for number 2. And then we'll do that for Z as well. But for now, we're just going to keep it simple. We are trying to find the cone of vision. So now we have the station point. We've got the center of vision. We have our 3 reference lines. We know the size of each of our horizon lines. We can now, since we have our station point, we can now start creating measure points, and we can find our cone of vision. But for sketches, all we're going to do is we're going to go for our cone of vision. And the general rule of thumb, which I've sort of developed over time, is understanding, because I see patterns fairly quickly. I've developed, or at least I've understood the pattern of the cone of vision. And the cone of vision, the mark that you make at 90 degrees or 30 degrees on each side from the eye, which creates a 60-degree cone of vision, that mark is usually just half of the distance line. So I take my station point, I take my center of vision, and I half that, and then that will essentially be my cone of vision. Now, those of you that have been following along with all of my other tutorials know that the cone of vision can be created, or always should be created, from the center of vision, right? So basically how the cone works is it takes the eye and it takes the center of vision, which is the line of sight, and then it says, all right, I need 30 degrees on this side and 30 degrees on this side, which will give me 60 degrees from the eye. So this is the cone that I can see things in. Anything that's outside of the cone will not be in the picture. Anything that's outside of the cone here will not be in the picture. So let's take this one up here. Let's take this guy. This is his line of sight. 30 degrees on the left, 30 degrees on his right, and then you've got his cone of vision. So that means that the only things that I'm going to be getting in the canvas, if I was looking in this direction from this point, would be anything that's inside the cone of vision. Anything that is outside of it will not end up in the picture. So this is a good way to tell what you're going to actually be able to have in your picture by placing, if you have a topographic and a side view, you can place a little camera in there and see where you want to see. All right, so now that we know what the cone of vision is, we know that in order to have standard perspective, or what we consider to be correct perspective, we need to draw within the cone of vision. As we've stated before, the cone of vision, if we have a canvas that butts up against the cone of vision, we're generally looking at a standard lens. If the canvas is very small inside the 60-degree cone of vision, then we're looking at more of a long lens, and I'll show you in a second. So we're starting from the center of vision, and then we're going outward in a perfect circle. And I don't know if you can see this, but I'm dragging out from the center of vision, and I'm making sure that the circumference of the circle meets halfway along the line that I'm now scrubbing against, right? So here's the station point. I want to make sure that this circle meets halfway between the station point and the center of vision. And right about there looks to be correct to me. So now I know, now that I have my station point and my center of vision, I know where my 60-degree cone of vision can go. And in general, if I build the scene inside this cone of vision, everything that I draw in here will be considered in correct perspective. Okay, so that is the basics of three-point perspective for sketching. All right, I will use this in part 2, which is coming up in a minute. I'll use this in part 2 in order to sketch the space that we've developed up here in this topographic map, or in this plan view and elevation. I'm going to use this. I'm going to create 4 different views of this three-point perspective grid. I'm going to use that to create 4 to 8 sketches of different areas of this kitchen in three-point perspective using this simple method right here. And then what I'll do is, once I choose the one that I like, then I can further develop it by creating the measure points, add my measure bars in there, and my true height line, my elevation. I can add all that stuff in there and start foreshortening my space, and then make my holodeck, and then build the scene out. But for now, we're just going to sort of guesstimate things. We're going to sketch. with the previous knowledge that we know, as long as we're drawing the space that we want in the end within inside this space, and we're using those vanishing points, in general, when we go to create our holodeck, our sketch will be very similar. All right, I'll see you guys in the next video.